Hello, my name is Alfie Keary and welcome back to part 2 of your Amoco module on the Internet of Skills with a focus on robotic teleoperation. I trust if you are listening to and viewing this recording, you've already listened to part 1, which is a general overview and introduction. In this part, we're going to drill down a little bit more into the specific applications of the Internet of Skills in the future, where we see the potential for all of this technology infrastructure in the future. And then we're going to look into, as this is an Amoco video training module, we're going to basically apply the Amoco architecture in the context of robotic teleoperation and specifically the use case we're involved in with our partners. I work for Tyndall, the Tyndall National Institute, and the other two partners on the project are Analog Devices and Endalo Technologies, and you can see their vision. Particularly, our premise on the Internet of Skills is that edge computing enhanced teleoperations plays a significant role in the concept of the Internet of Skills. So we believe that edge computing and resulting teleoperations infrastructure is going to drive that fundamental change when we move from the traditional internet of data and knowledge to a highly interactive internet of skills on a global scale. And we're saying that that is going to be an extension of Internet of Things and the Internet of Robotic Things. So we are now currently experiencing the Internet of Things. We really are only starting to experience the Internet of Robotic Things, and all of that will come together in the future under the umbrella term of the Internet of Skills. We're going to have a quick look through a selection of use cases. I'll go through these slides fairly quickly because any one of these could relate to what you're going to see presented here in our use case 3, which we've been working on in the Amoco project. So some of these you already know about. This robotic surgery, remote tele-robotic surgery is already a large area, but a large area of technology development, let's say, in the medical field. But the true potential of someone in thousands of miles away being able to perform an emergency procedure, it's few and far between. We are not there. Realistically, we are not there. And for the foreseeable future, it's going to take a number of technology shifts before we can actually move towards that direction. Unmanned aerial vehicles are ever increasing, and particularly we've seen both positive and negative outcomes of drone technologies in the past number of years. So this is particularly a major use case area. Autonomous vehicles. Yes, there's a lot of hype around self-driving cars, but tell me cars driving in the dark, tell me the complexities of cars really driving in this very, very challenging real-world scenarios. I think most technologists will agree that the technology is advancing, but we have to look for major innovations before this becomes a reality. Underwater remote vehicles is another aspect. All of these things, you can see telepresence robotics, they're all starting to actually become independent domains in their own right, using the typical teleoperations technology and the IoS suite of infrastructure that is under development currently. So use cases and particularly remote industrial machine operation. I've already talked about the telemining example, and you'll see ever increasing opportunities in this type of remote industrial machine processing and operations. Space is going to really be transformed with the potential for these technologies. Agricultural automation, particularly in the last 12 to 24 months, we've seen major advances in all forms of automation in the production of food for the agricultural sector. So again, major opportunities here, the environmental monitoring side of things, and the management of highly harsh and complex environments, which basically may not be safe for humans to actually conduct their work near such facilities as nuclear facilities. So you can see so far there's 10 dedicated use cases that will all be impacted by robotic teleoperation and the emerging Internet of Skills. One final slide now. And here, construction machinery can be manipulated remotely. Mining operations I've already talked about, and the tele-operated inspections using drones. This will be very relevant when you're looking at land usage, when you're looking at emergency response. So all of these type of specific applied applications of drone technologies are being enabled by the technologies we're discussing in this module. Disaster recovery is another very specific area. And finally, there are many other use cases to be considered, invented. So can you think of any other use cases that you think where robotic teleoperation may be relevant, or where skills can be transferred and accessed remotely? Having looked at the use cases for Internet of Skills and robotic teleoperation, we now refer back to what this education module is all about. It exists because of the IMOCO project, and a very brief revision. The IMOCO project is made up of the architecture. It's made up of 4 layers, and layer 1 is where all the sensors, you can see all forms of sensors are accounted for. These sensors may be traditional electronic components with microelectronic sensing capabilities, but increasingly the sensors are acquiring onboard intelligence and decision making. So the next layer is the decentralized controllers. So all of these have got to do with some form of motion management, motion monitoring and control, particularly within a manufacturing production process. Then we move up into layer 3, which is system behavior layer. And in here, this is where you're going to see increasing forms of intelligence. So it is managing the behavior, the outcomes, and the status of a particular industrial process. And this is where things like predictive maintenance, diagnostics, process control, tuning, feed-forward controls, etc., are all coming into this particular layer. We will discuss this, but you will see that particularly between layer 1 and 2, there's ever increasing requirements for intelligent self-determination, intelligent-based behavior within the processes that take place in layer 2 and layer 3 of the platform. And finally, layer 4 is the digital twin layer of the IMOCO architecture. And this is where, for the want of a better analogy, is that what is represented in layer 4 is a complete digital representation of what happens in layers 1, 2, and 3. That's the long-term goal of digital twin technology as it evolves over the coming years. So that is a review of the IMOCO 4-layer architecture. Now, what we're looking at here is particularly use case 3. So UC3 is our use case, and we are working, our three partners, ourselves, Tyndall, Mdalo Technologies and Analog Devices. We're working on the proof of concept and applying the Emoco 4 layers to develop a teleoperations platform that could be used in all various aspects of the Internet of Skills. So I'm going to briefly review the architecture of our use case, and this is our local end, and typically think of the local end as where the user is. I'm not going to go into additional detail, but very, very briefly, like the original Emoco architecture, we have sensors in layer 1. Then when we go into layer 2, we have some form of processing to do with the data streams that come in from the various sensors. And some of these sensors will have onboard intelligence. So for example, we use a time of flight sensor. It's a vision camera, which is able to pick out depth fields within an image and identify a human frame, a human hand, a wrist, and also potentially objects which are captured in a frame of data. We also have a glove, which is used for very fine-grained manipulation of a robotic finger, robotic arm. Sorry, I should be saying a robotic hand, because you have the finger manipulation on the robotic hand. So here we have layer 1 is the sensor feeds, layer 2 is where the data is processed, and there's certain aspects of AI introduced here, but primarily we keep the behavior aspects of our platform at the local end. So there is applied AI analytics which are deployed into the robotic teleoperation platform at layer 3. And then we have specifically at the layer 4 is where we have developed a proof of concept for a digital twin. Digital twin has a major role to play in teleoperations. In our particular use case, we have done a certain amount of engineering work on it in terms of to show how it can represent the robotic teleoperation. And we'll talk about that briefly, and we have some demonstration videos for this. One of the things we didn't discuss is building blocks. Building blocks are core to the Emoco architecture, and there are 10 building blocks. I won't go into each one, but our use case primarily relates to building block 1, which has to do with edge components. We work in building block 3, which is novel sensors, so various types of sensors, and building block 8, which is AI algorithms. We're also see potential for our work in building block 6, which is preventive maintenance and condition monitoring. So that is very briefly a, I suppose, non-technical overview of the functionality of our use case at layer 1 in the context of the local end. Next, we're going to look at the remote end. Really, the layers, of course, are the same. At layer 1, we talk about the robots and the data flows in terms of coming from the local end of the platform. The sensor data is processed and communicated and sent to the remote end, and this could be 1 kilometer, 1,000 kilometers, 10,000 kilometers apart. The building blocks are the same, so building block 1, 3 and 8 primarily we relate to when we refer to the Emoco project. And then there is, once the data is received, there is processing that happens at layer 2. So the data comes from the local end. We use this as L, and there is processing that happens in layer 2. And there is also potential for AI processing to happen in layer 3. Currently, we are not doing a lot of work on the AI aspects of the remote end, but in the future, for example, we could have object recognition or robotic state awareness, so the robot knows the state it's in, which could help it identify the next state that the robot should position itself in. So there is potential to build in AI services relating to the robot movement and vision capabilities into layer 3. But once the data is processed, that data is fed down, and the various activators are, in this case, a robot arm and a gripper receive the data, and it carries out a predefined action. There is no digital twin in the remote end of our platform. That is primarily being provisioned into the local end of the use case 3 platform. I've talked in an abstract way about the Emoco project, the building blocks, and the local end and the remote end. This is our robotic teleoperation platform, and it gives you a sense for, I suppose, all the different types of hardware and software components that are required. We use sensors up here. This is the time of flight sensor. This is a motion tracker sensor, a Vive tracker. And we have the Tyndall glove. All of these have different interfaces, and they are all interfacing in some way with an edge device. We work with the Polar Fire, microchip Polar Fire edge device, and we're also working with the STM32 edge devices in our project. The lower part here, this is the industrial protocols, and specifically we made a decision to work with the Siemens PLC, which supports the Profinet industrial edge-to-edge protocol infrastructure. And we also work in order to connect our edge devices into the network, the Profinet network. We use a device called the Analog Devices, ADI stands for Analog Devices, and they have a module called a RAP-ID module, which is configured such that we can communicate data back and forth from the local end to remote end. So this is really an overview of the edge infrastructure for our use case 3, the sensor layer at the local end. Next, we look at the remote end of the platform, and I don't have to spend as much time. I've talked about the Profinet, and this is really the data is transferred across the Profinet, and you can see here there is Cobot control commands. Cobot stands for collaborative robot. So the Cobot, the control commands are received by the edge components, whether it's a microchip, Polar Fire, or the STM32 type of edge devices, or indeed other future edge devices could be built into this platform as edge components are constantly evolving. One of the positive things about the Polar Fire is the embedded AI processing capabilities and the brute force power of this specific Polar Fire device. And that basically is where the robot is connected in. And as we'll see in part 3, the various videos, these edge components are directly sending the data and feeding it into the various robotic movement using the arm and the gripper. I don't know if you can see it there, but you can see the actual gripper manipulating a series of blocks on a tray. So that gives you an overview of the high-level Emoco architecture. I've covered this in 2 slides, the local and remote end. And then this is more practical, so it demonstrates at the local end what all of the hardware components are and how they're interconnected. And this is clearly the remote end where we have the robot sitting and being manipulated. This really is a summary. It's referring back to a practical overview of our use case, I suppose in a non-technical way. It's just summarizing the 2 ends, the local end and the remote end. We have got some form of industrial controlling going on here using PLCs and various edged components. And then there's a layer 3, which we see layer 3 as being primarily embedded AI, But I will point out that the AI filters right down the platform. The AI filters across layers 3, 2 and 1, and also in the future AI will be very, very important component of true digital twin infrastructure. That's most certainly going to be the case in the future. Now, here are some screenshots, and you will see these again. I suppose it's like a review of the videos you're going to see in part 3. This is one of our researchers, Owen, and in the very early stages of the project, we built the whole robotic teleoperation platform using a dedicated PC device. It wasn't on the edge components, and we built it in our labs at Tyndall. And think about it, this is Owen wired up with the Tyndall glove for precise finger manipulation of the robot gripper, and he's using a Vive tracker to move the arm of the robot. So that was really work we did as proof of concept. And here you could think of Owen being located in, for example, London, and the robot could be located in Germany. So that would typically be a scenario that we have simulated in our lab. So the local sensor end to the remote robot end. This is the work that is ongoing on the edge-to-edge infrastructure. Think about these look like two bridges. They look like, so if you think of them as being bridges, and between those two bridges could be anything from 1 kilometer to 1,000 kilometers, or indeed 10,000 kilometers. I go back to that scenario again. So think of them as bridges, and there could be any scale of distance between them. And what you see here are the edge components. We've got the STM32s, we have the PolarFire, we've got the Siemens PLC, and all of these are, they are set up in the lab at Tyndall, but you can think of them as being distributed at a distance. But that is really the edge-to-edge infrastructure that we've set up in our lab, and in the future we'll be testing that, and particularly aiming to address and identify how latency can be improved when we want to send a signal from one edge device, one edge part of the platform, to the remote edge part of the robotic teleoperation platform. I've included a slide on digital twins. I'm not going to go into any detailed discussion, but I think we just did some initial research on digital twins, and we created a model of the robot, which is not too difficult because we work with the universal robot, UR16E, and the manufacturer supplies a digital framing of the actual robot itself. So we did a little bit of work around with that, and we introduced the gripper. You can see the fingers of the gripper here. So really, a lot of this work was conducted in Unity, which is ever increasingly being used for the development of digital twins. So that's a space to watch in the future as the Unity platform matures and improves and targets the digital twin markets of the future. So here you can see the robot, you can see the gripper. The actual blue hand is a representation of our researcher as he was moving his arm in 3D space. So that's what that is representing actually. And then we have a series of blocks here represented, and we just tried to start doing a very simple block manipulation task. And Owen, who was working on this project very much in the first year, realized that how to represent the remote end of the platform in the digital twin at the local end is extremely complex. And even to track the work that you're doing at the remote end, in his case, it was moving a few blocks around the table. we had to have some form of sensory capabilities on those blocks. And what he came up with was he put the Vive trackers onto the actual blocks themselves. And that was then being able to feed data back into the digital twin. I'm not going to spend any more discussions about digital twins, but it's sufficient to state that there are considerable challenges and opportunities when we try to introduce digital twins into the whole complexity of robotic teleoperation. It's not impossible, but it is going to be an area that will need a lot of technological developments. I've listed a number of them. I'm not going to go through them in terms of the detail, but things like how to represent the world at a remote end, object detection and representation. That's how true life objects can be represented as virtual objects in a digital twin virtual world. But we have to go down this road, because a true digital twin of a robotic teleoperation world offers amazing opportunities for the Internet of Skills in the future. So this is possibly the roots of a future module in digital twin technology in the context of robotic teleoperation. The work of Analog Devices was conducted in their Catalyst lab, and particularly they played a major role, and one of my colleagues, Nihal, here, as you can see in the center video, has specifically done considerable research, focused research on using the time-of-flight technology. I'm not going to go into the details of explaining how time-of-flight technology works, but Analog are specializing in using time-of-flight vision systems to drive robotic components. And particularly here, as we'll see in the video, you'll see how Nihal uses her wrist to actually drive the robot in a X, Y, Z space. And that's the type of research that is very specific to Analog and the technologies that it is delivering to the Internet 5.0 in the future. MDALO Technologies are AI specialists, and particularly embedded AI onto the polar fire device. And one of our colleagues, Alan, a specialist, a data scientist, machine learning specialist, has explored a number of areas, and we are looking at hand movement prediction. You'll see this in one of the videos. We think hand movement prediction can very quickly put a remote robot into a required state, and thus reducing the amount of data that has to be transferred in order for it to carry out a particular operation. So we are doing some basic work on gesture recognition, but once this work is in place, we can expand that into more complex gesture-based targeting of the robot to carry out certain roles. So that's particularly the gesture recognition work that is going on. Secondly, we're also looking at innovative techniques in terms of how can we predict the real-time direction of a user. How can we predict where their arm will move and that it moves smoothly so that the robot can actually progress to do a particular task. And our ambition would be that the robot is exactly in its final destination at the same time the human user has relocated their arm or their wrist to a particular space when they're trying to solve a remote teleoperation problem. So in a nutshell, this is all about prediction. So can we use prediction capabilities, AI predictive capabilities, to, I suppose it's a very, very challenging task, to best guess what the user is going to do when they're carrying out a specific predefined task. And that is the challenge of AI on the edge, and how it can be used to reduce latency in the teleoperations process. This is just a quick run through of where we take AI algorithms which could be running in the cloud or on very sophisticated dedicated PC servers, but increasingly the edge components are providing dedicated capabilities, both hardware, chip capabilities, silicon on the edge device itself, to do with the model, the complex model manipulation and the parameters that have to be manipulated when you're looking at any of these machine learning models. And they are being optimized down for these specific edge devices, and particularly the microchip's polar fire component uses what's called a vector blocks accelerator to reduce down the inferencing requirements on the edge device. It reduces power and it makes things work a lot quicker. So that's a little bit into specific detail, but it gives you an idea of the type of things that are happening and have to advance in order to give low power, highly complex AI inferencing on edge components. So that is just about to wrap up our part 2 of this module. These will be the videos you'll see in part 3, and they were compiled for our demonstrators in Eindhoven, which took place in November 2023. They are short videos, and generally they follow what I've already introduced in this particular video. So you look at the work in Tyndall, you look at the work in the Catalyst Center, and you get some idea for the complexities of the AI work that is being conducted as well as part of the use case 3 teleoperations project work. Okay, so that wraps up part 2 of our education module on robotic teleoperation and its role in the Internet of Skills. I would strongly recommend that you have a look at the videos in part 3. I talk over some of the videos as well just to explain what's actually going on. A lot of it probably relates to what I've already discussed in this module, but it would be good for you to see the various components and the various research that has gone on in the EMOCO project under use case 3. So I look forward to you viewing part 3 of this module, and then I will talk to you again when we wrap up in part 4 after you have had a chance to view the videos. Thank you for listening, and talk to you soon.